Well, hi everybody and welcome back. This is a little follow-up video like I promised on the transistors and some of the things about what this uh, Sansui AU-X1 is all about. First of all, let me say that I'm coming to the conclusion that the Sansui AU-X1 is the Bugatti Royale of amplifiers. If if any of you have not heard of what a Bugatti Royale is, you may want to look it up. Actually, I was just at the Henry Ford Museum about a week or two ago. I was on a job out in Michigan and had an employee with me that had never been there. So I said, well, why don't we just do a little boondoggle there, a little side trip, and I'll show you the museum. And of course, they have an example of a Bugatti Royale. It's one of only 6 ever built. It's a car, and look it up. It's an interesting story. But bottom line is, just like the Bugatti, the amplifier is really big, really heavy, very luxurious, and when it works, it's really something to behold, but that's only when it works. So anyway, all joking aside, how do I get on all these crazy tangents here? I don't even know why you guys even watch this half the time. Anyhow, let's get back on topic. This video, we're going to talk a little bit about the AU-X1. The first thing you need to understand was what was the purpose of designing the amp the way they did. And the reason is a new buzzword that came up at the time called TIM distortion, T-I-M. And that's an acronym for Transient Intermodulation Distortion. So what is Transient Intermodulation Distortion? Well, we're familiar with intermodulation distortion, which is when you have two, for instance, the way you test for IM distortion is you take two tones. One of them is like, I believe, the 60 hertz sine wave mixed with I think it's a 1 kilohertz or 3 kilohertz. I can't remember. It's a higher frequency, like 3 kilohertz or 6 kilohertz. I'll put it in the make a little message on the screen here when I'm editing this. But it's a low frequency and a high frequency. And the low frequency is, I believe, one of the frequencies is a factor of 4 to 1. So one frequency is 4 times the amplitude of the other. And essentially what you're doing is you're measuring the spectrum on it and looking to see if it reproduces those two frequencies properly or if it makes all of these other harmonics that will show up as distortion. It's something that again, there's ways to test it. You really need the right equipment and so forth. But to the next level, transient intermodulation distortion, the best way I could explain it or can understand it is that when you're having a change in a complex waveform, the ability of the amplifier to reproduce that without distorting it. So for instance, you can actually, even though the audible frequency range that our ears can hear is between 20 hertz and 20 kilohertz, that's the average human ear that's healthy, healthier than mine, can hear, is that 20 hertz to 20 kilohertz. But whenever you combine a bunch of different complex waveforms together, not just sine waves, but sound, like listening to my voice or listening to music, it's no longer a pure waveform. It's what's called a complex waveform. And that waveform, even though those sounds are in the audible frequency range, the actual shift of amplitude during that period of time can be much higher than 20 kilohertz, believe it or not. In other words, you can have a very rapid change in amplitude over a period of time, even though the sound that you're hearing is in the audible frequency range. Does that make sense? Makes sense to me when I think it, but doesn't make sense to me when I hear myself saying it, if that makes sense. So anyway, let's just demonstrate something, okay? And what I'm going to do is I'm going to play a very unpleasant sound into the microphone from my my signal generator. So take a listen to this as I turn it on. I won't play it for very long, and if you're wearing headphones, you may want to turn the volume down a little bit. Okay, now that was a very annoying sound, and I'm just playing it right out of a speaker here I had sitting on the bench. And if you listened very carefully, you can scroll back and listen to that tone again. It's not a sine wave, it's not a square wave, okay? It's a complex waveform. And if you try to capture it on an oscilloscope, that waveform kind of looks like this. Let's take the glare off and let's zoom you in. And you can see now when you're looking at it, that is not a standard looking waveform. And what we're talking about is, in order for an amplifier to properly reproduce this sound, there's some pretty rapid events taking place. If you look here, you have a ramp here, then you have a very sudden drop in amplitude, and then you have this little spike right in here, see it? And then it comes back, it ramps up, then it ramps back down, and there's a curve here, and then there's a very rapid rise in amplitude, and then a very rapid drop again. Now, of course, playing this out of a signal generator directly into a 300 megahertz oscilloscope, we can show this very easily. The problem comes into when you try to reproduce this through an amplifier, because an amplifier, you got to remember, has a lot of different components that this signal has to pass through before it finally gets out to your speakers. And this is what transient intermodulation distortion is all about, is that because during certain points of this waveform, there is a very rapid change in amplitude and voltage. Because of the capacitance and so forth contained in a lot of the components in an amplifier, this will get distorted. In other words, these very rapid amplitude changes will actually have a little bit of a slope to them. Okay? Now, the ability of a transistor to be able to do that is called its slew rate. And this is something that is very important when we're trying to reproduce very complex waveforms. Now, most transistors that we work with, for instance, our MJ15013, what is it, 15013 and 15014 or something like that, the big TO3s. Wait a minute, let me get one. Okay, so here's a big old NPN that's not in focus. Let me back off a little bit. There you go. It's an MJ, what is it, 21194G. You can see, there it is. So for instance, this transistor, it actually is considered a very good quality audio transistor, but it is limited in its frequency response, and therefore it would have a difficult time reproducing things like this perfectly. Now, let's talk about transistors, how these things are rated. So I'll focus you back on these ones right here. So the first thing we have to worry about is the slew rate of a transistor or any semiconductor, and that's the ability for it to make those rapid changes. But there's also another property in a transistor called transition frequency. Now, what's transition frequency, or FT? Your transition frequency, the way a transistor works is as you put a higher and higher frequency waveform through the transistor. In other words, the transistor is not operating at DC. It is actually operating at a changing signal. I'm calling it changing because it's not AC. AC means alternating current. We're not reversing the polarity. All we're doing is we're making a rapidly changing signal, a waveform. And as the frequency of that rapidly changing waveform increases, the gain of that transistor decreases. So a lot of people don't realize that. When you're reading the HFE, depending on the type of test equipment you're using, if you're using something that applies a DC voltage and you measure mathematically, that would be the HFE at DC. But as you start applying a waveform to it, for instance, like this Peak Atlas unit, I believe, like these kind of devices actually put out a waveform at a certain frequency. A lot of them tested at like 1 kilohertz. And so when you see the HFE reading, it's at a 1 kilohertz frequency. But if you were to increase the frequency of that test signal, you would notice a decrease in your HFE, or your forward current gain. Now, the transition frequency, okay, is the frequency at which the gain becomes unity. That means the point at which the transistor no longer will have any gain to it when you apply a signal to the base. There will be no gain. That's your transition frequency. So every transistor data sheet will show you the FT. And most of them, like that one I showed you, is anywhere from hundreds of kilohertz to a few megahertz. Now you might say to yourself, why do I need a transistor that, goes up into the megahertz to reproduce sound that's in the audible frequency range, like 20 kilohertz or lower? 20 kilohertz is much, much, much lower than, for instance, 4 or 5 megahertz. So the reason being is what I just showed you. That whole property of how a transistor works with the slew rate and the transition frequency, they're kind of connected to one another. So the lower the transition frequency a transistor has, the less its capability to reproduce very rapidly changing signals it has. So that's what the whole idea behind transient intermodulation distortion is. That's just a big fancy word that says the transistor can't keep up with the rapid changes of a complex waveform. Now, a lot of people can't hear that. If you're just listening to a song or something and you don't have a real high-end set of speakers or whatever, you may not hear the difference. But what they set out to do with this amplifier was to address the problem of transient intermodulation distortion. In other words, they were trying to come up with the least amount of that distortion as possible, and the only way you can do that is by using very high frequency transistors. Now that's a problem, because the physical property of a silicon transistor, or any transistor for that matter, germanium, whatever, is that the higher the power density a transistor has, like the higher power handling capability it has, just by its nature, the way you have to build the transistor, the lower the frequency response of the FT of that transistor is going to be. So it's very easy to have a very small signal transistor, like this little guy right here. This is a 2SC 1845. These can run, I didn't look it up, but I'm sure this runs up into the 100 megahertz or above range is its transition frequency. So this would be very good at passing a signal and not causing any transient intermodulation distortion in the audible frequency range. The problem is that other big transistor we were looking at, that MJ, 21193, it does not have as high of a frequency, and it will cause distortion at certain points. These transistors, however, are very special, and they have a transition frequency for a high power transistor of 60 megahertz. Now 60 megahertz is much higher than 4 or 5 megahertz of, a standard power transistor, or even lower. Some of the transistors on some of the older units are much lower than that. Some of them are only a couple of 100 kilohertz is their transition frequency. So that's why these were designed around this whole technology. Everything in the circuit for this is high frequency transistors, including the outputs. Now, there's nothing perfect in life, and of course everything has its trade-offs. And one of the trade-offs that we're going to talk about is, if this transistor operates at very high frequencies, it can pass very high frequencies, even unwanted ones. And these transistors, because of their high frequency capability, it's much easier for a poorly designed circuit to go into self-oscillation. We call that parasitic oscillation. It's an oscillation that's a parasite on the circuit. And that parasitic oscillation is bad because it can run at very high power. And since it's above our audible frequency range, those oscillations can be up in the high megahertz range. And since it's in that RF range, you don't hear it, but it is actually causing the amplifier to run at levels way above the ratings of the transistors, and they burn up. So by its nature, in the old days, conventional power amplifiers were built with transistors that had a low transition frequency, and because of that, they wouldn't be susceptible to high frequency oscillation. Even if the circuit had a lot of loops in it, ground loops or whatever, that could oscillate at very high frequency, the transistors could not oscillate at those frequencies because they couldn't pass those frequencies, so the amp would never go into oscillation. Once you start dealing with high frequency transistors like this, all of a sudden you see the errors of the design. And that was one of the problems with this amplifier. It solved one problem by reducing transient intermodulation distortion down to a minimum, but it created a problem by allowing the amplifier to very easily go into self-oscillation. Now then, that's where all these problems are with these black film capacitors and all this we were dealing with. Now, another thing you need to know is, in order for these transistors to work properly, you have to be able to put the high frequencies into them. And a chain is only as strong as its weakest link. And if you remember, there are a whole bunch of transistors on this board, including these guys down here. And several of you, thankfully, caught me on a problem that I have, and that is, two of the transistors I used as replacements in this circuit, okay, did not have high enough frequency to pass those signals through without adding transient intermodulation distortion. And it was these two here, TR16 and TR15. All the other transistors I used were high frequency ones except these two. And where were these situated? Well, they were situated right here. These are our driver transistors, 15 and 16. Notice they're the ones that directly drive the outputs. So guess what? If these guys will block the really fast transient changes in a complex waveform, that sound is never going to pass to these, and it defeats the whole purpose of having these fancy transistors in here. So there you go. So thank you guys for catching that. I received one email from a gentleman named Sergio. Sergio, I want to thank you so much. And several of you also put in the comments section. So just so you all know, I am ordering, or have already ordered, the correct 2SA and 2SC transistors to replace these with the proper replacements. The reason I am replacing all the transistors was this amp has been worked on. It's obviously had damage in it. I don't know the state of these transistors, and I don't want to put it all together and have something fail. So that's why we're getting new silicon in here. Okay, so what makes these so special? Why can they run at 60 megahertz and our other good transistors cannot? Well, it all has to do with the process of how these are built. Again, like we said, small transistors are very easy to produce with high frequency, high transition frequency in the manufacturing process. The problem comes into when we start to have high-powered transistors. And, well, a picture's worth 1,000 words. So if you remember from our notes, our little viewer comments and notes video from a couple weeks back, we talked a little bit about these transistors and how they're built, and really the purpose of that one was to kind of show the difference between the real transistors and the fake ones and so forth. So this is an actual RCA, a late model RCA 2N3055. This one actually has a higher transition frequency than the original 2N3055s, but it has a much lower transition frequency than any of these Sankins up here that we were looking at. Now I'm going to try to zoom you in real close. If you take a look here, do you see that little die there in the middle? You see it right here? Right there. You notice how there's like these little zigzaggy lines in there. See how close I can get. See them? Hopefully I got it in there in a way you can see it. And get some better light on the subject. So there it is. You see them? It's kind of like two E's that are like fitted together like that. Those are your PN junctions. And those are called finger junctions. And I may not be using the exact scientific terminology for this. You have to forgive me because, again, I'm not an authority on transistors. I don't know nearly as much as some others do out there. So any of you who are more versed in this, please go into the comments below and embellish upon what I'm saying here or correct me in what I'm saying wrong. But anyway, so these finger junctions, you see, that's the standard process of making these power transistors. And you notice they're actually relatively large for a transistor. And because of that, that causes capacitance, a capacitive component in there. And right there is what causes the problem. That capacitance actually creates a delay in this thing turning on and turning off and changing voltage levels very rapidly. So that's a limiting factor. Now, what Sanken and Toshiba and Fuji and several other companies came up with, there were quite a few out there, believe it or not, I think even Motorola, they came up with several different processes in order to reduce that capacitance. Now, there's two main ways that we do it. Okay, and that's what we're going to talk about. We're going to talk about the LAPT type process and the ring emitter process. So let's take a look at that first. So the first thing we're going to look at is the ring emitter type transistor. So as you remember from looking at this one, those are called the straight finger junctions. And as you notice, they look like this. And of course, what do you have when you have junctions? You have capacitance. Okay, so what we want to do is we want to kind of reduce that area. So they worked with some different things. The first one they came up with was a horseshoe type junction. And you have your P and N junctions situated around. So this center part is your emitter, I believe. Or is it your collector? Or no, maybe the base. I don't know, guys. Help me out. Anyway, the contact area is here and here and here. And if you notice, you have a different amount of area the way this is situated. And what it does is, being in this ring, semi-ring area, they call this a horseshoe, it actually reduces that capacitance and increases the transition frequency of the device, even on a large device. You can actually cut this die thinner so that it will have lower capacitance because of the way this thing's designed in a ring area. Now the next version is called a Pac-Man, and you see what they did here is they actually, this center area is now completely encapsulated, and then the other junction is doped on this way here, but you still have an opening here. And then finally they came to the process called a true ring emitter, and that is where the emitter is a complete circle around the base, just like that. Okay, so this was a majorly improved version of power transistor, allowing you to have high frequency and allowing you to have be able to use that high frequency to minimize your TIM distortion, or your transient intermodulation distortion. The next version we're going to talk about is what we have up here. And remember when I told you that I wasn't sure if these Sansui transistors were ring emitters or not? I thought they might be, but they weren't. It turns out they are not. They are actually LAPT process, which stands for, and I highlighted it for y'all. I printed this. This is straight from Sanken's website, okay? You can look it up. You can go to their website. They have so much information on the process, you know, how they produce transistors and so forth. And it stands for Large Area Parallel Transistor, okay? And essentially what that means is, as I told you earlier here in the video, it's very easy to make a small, low power, small signal transistor have a very high transition frequency. So the idea with this was, why can't we just take a whole bunch of those and parallel them onto a die so that you have the high transition frequency, but you have the higher current capability of a power transistor, because all these transistors work in parallel. So these are LAPT type transistors here, okay, these Sankuis, and that's what they're using in the AU-X1. And again, these ones can work up to 40 megahertz, but even higher, these ones up here even work into the 60 megahertz range, which is pretty good. So that's why if you were to take a standard power transistor and put them in place of these, or you were to take a lower frequency driver or preamp transistor and put it in place of one of these, the amp would lose all of its magic. Because what would happen is it would defeat the purpose of what they were trying to accomplish. Now the other thing that doing this does is it allows the amplifier to be designed to have a lot less negative feedback. So when you look at the amount of negative feedback in this amplifier, it is lower than the amount of negative feedback you would see in a standard design of amplifier. So there again, by not having the proper amount of feedback and not having the proper frequency transistors, this amp actually won't sound very good. So it's an all or nothing thing with this amplifier. Again, I could put MJ 21193 and 21194s in there, and it would work perfectly. The amp would come on, you would be able to play music, and it would not go into parasitic oscillation nearly as easily. So it would make the amplifier more stable. However, that sound, that very clear open sound stage that this thing is known for, and you have to hear it to understand what it is, would be gone. So again, this is an all or nothing amplifier. It's useless if you put the wrong silicon in here, which is why Sansui went through all this trouble to design this amplifier around these transistors. Unfortunately, in my opinion, they failed at doing that. I think that this thing was rushed to market, and later versions apparently dealt with it better and were more reliable. And there are modifications that can be made to this amp to make it reliable, so you don't have to worry about it. But bottom line is, when it's working, the sound is amazing on these, from what I understand. I've never heard a properly working one ever. So this will be a first for me. I can't wait to hear it. But also, we have to make sure that we don't allow those situations where this thing can go into oscillation. And part of it is all those little bypass capacitors. They're designed to snub out the ultra high frequencies, but still allow enough of the transients through that you don't get that TIM distortion. And it's a delicate balance. That's why if you notice, some of those caps we were changing in there were 1 picofarad. And even increasing that to 2 picofarad would change the sound of this amplifier. Even though those little capacitors are not directly in the audio path, they can actually attenuate the audio path if they're the wrong value. And conversely, if the value drops because the capacitors go bad or wear out or fail, all of a sudden the amplifier is highly susceptible to, you guessed it, parasitic oscillation. So it's a delicate balance. So that's why I used very high quality ceramic NP0 capacitors that were very small surface area but still had a high enough 200 voltage rating. And hopefully between that, careful cable placement, wire placement and everything, we will be able to get this to be a perfectly working amplifier and have that sound that we're looking for. So this was a long-winded talk about transistors. Some of you are probably bored to tears by now, and some of you hopefully, answered some of your questions, because it's a big topic to talk about, and it probably requires somebody smarter than me to really explain it well so that it's understandable. But anyway, that's what we're talking about with these transistors. That's the difference between a standard bipolar transistor, a ring emitter transistor, and an LAPT processed transistor. And I hope you understand what TIM distortion is, what this amplifier does to deal with it, and how these transistors were made. That's really all I'm trying to get through this video. So again, I thank you all for listening, and I thank you guys big time for catching me on that. I did not catch that, those 2 driver transistors. I did not catch that they were only 4 megahertz transistors. That would have kind of defeated all the purpose, and I probably would have been all patting myself on the back how good I did, because it doesn't go into oscillation, when probably it may have been, who knows, I may not have even fixed anything, but by putting those transistors in, who knows. So anyway, thank you again. I hope this was a little bit informative and cleared the air with some of this, how this works. And I'll be coming back very soon with the next part in this series. Thank you guys, and take care. Be well. Bye-bye.